Okay. Yeah. Okay. Now it should work.
Okay, thank you. Please be seated. Ladies and gentlemen, welcome to the public doctoral defense of Nikhil Prabhu. I declare the session open. Nikhil Prabhu obtained a master in mechanical engineering at Linköping University in Sweden. He has submitted a thesis to the Faculty of Engineering Science entitled Micromechanical Modeling Strategies Toward High-Fidelity Digital Twins of Polycrystals. And this is part of the requirements for the degree of Doctor of Engineering Science, PhD. He will now proceed to defend his thesis. Nikhil Prabhu, you're invited to give a presentation of approximately 45 minutes about your work. Following your presentation, there will be the time for discussion of your work with the members of the examination board and with the audience. Nikhil, the floor is yours.
Thank you. Okay. Good afternoon, and thank you very much, first of all, for attending it physically, and also people who have joined online. Yeah, thanks for attending. And it feels nice to see many familiar faces in the audience. It also helps a bit with the nerves. So in this presentation, over the next 40 minutes, I'll be giving you a general overview of my thesis. So without going into much of technical details, I'll be covering from experiment to simulations and from understanding and calibration. I'll be mainly focusing, as you might have gathered from my title, how modeling strategies at micro scale simulations. And there, let's begin now this presentation, not with an experiment or a simulation, but with a story. A story which some of you might recognize, a story which showed the world the power of virtual replicas.
Okay, Houston, we've had a problem here. This is Houston. Say again, please. Houston, we've had a problem. We've had a main beam unable.
So some of you might have recognized this voice clip from the incident itself or from the movie that was based on this incident. So it was April 1970. NASA was on its way to land 3 of its astronauts on the surface of the moon for the 3rd consecutive time with their Apollo 13 mission. And it seemed like everything was going well until they got this signal from the spacecraft. So what had happened? An oxygen tank on the spacecraft had exploded. And you might be thinking that oxygen is quite important in the spacecraft for breathing, but in this case, it was used for breathing as well as it fueled the fuel cells which powered the electrical systems. So in no time, the spaceship, which was almost preparing its landing on the moon, lunar surface, was now a stranded, damaged vehicle in space with limited oxygen, which meant limited fuel and also limited time. So the astronauts had to now carefully choose a maneuver so that they can abort the mission and go back to the Earth's surface. And this, they had to do it very judiciously because they had limited resource. So the mission control on the Earth, they were receiving continuous telemetry data from the astronauts, from the spaceship. And what they tried to do was, with these simulators that you could see, they tried to recreate the situation of a damaged spacecraft. Now, these are not purely computational one. As you could see, there are mechanical actuators and also analog sensors and a lot of human expertise involved. So what they tried to do is recreate the situation of a damaged spacecraft with the help of these simulators. So these simulators formed what we nowadays call virtual twin of the real spacecraft. Unless this was not really virtual because this had a lot of mechanical components involved. So what they tried with these simulators, they tried different scenarios and figured out a good maneuver that the astronauts could use to successfully get back to the orbit of the Earth and then come back home safely. So what NASA did back then was quite remarkable. And it was also one of the most significant and remarkable demonstration of what we nowadays call digital twins. While the term digital twin did not exist when this incident happened, but the idea was already there. So the three key components which we can identify there, the spacecraft, which form the real system, and then the simulators on the Earth, which form the virtual replica, and the continuous communication between the mission control and the spacecraft through telemetry. So, so we also try to apply the same concept, but in a different context. Not really to bring the stranded astronauts home, but to understand and model material behavior. So before we go into broader details, but let me first define what we mean by digital twins. So a digital twin of a real system is a virtual replica, not just a structural one, but also a functional replica. So it consists of three key elements: the real system, which could be a turbine engine, as you could see here, and also a digital model, a computational model of a turbine engine, virtual replica, and an information channel that connects the digital and the real world. And here, this information channel acts as a closed feedback loop. So the data from the real system goes into the modeling, upgrading and calibrating the virtual replica, and the predictions from the virtual replica is used to make decisions on the real system. So these are quite widely used in industry, for example, for product design and performance optimization. Now, if you consider this wind turbine as an example, it's usually quite up in the sky, and these are quite heavy. So carrying out performance monitoring like manually would take a lot of effort. So usually digital twins help here to reduce the effort in this case. And also digital twins can be used as complement to experimental data. So these cannot replace, but they can act as complementary. And also digital twins are quite important. And but there is a problem here. These digital twins are usually based on macroscopic models or based on performance metrics, which are quite empirical. So the idea is they often disregard microstructural features, and therefore, because they disregard these microstructural features, they lack predictive capabilities. And my thesis actually aims to include mesoscale modeling strategies in multi-scale simulation so that the hierarchical nature of material is captured in these digital twins. So what I mean by hierarchical nature of material behavior is, let's consider a turbine system, which is a system of maybe thousands of components. And then if we isolate one component, such as a turbine blade, so this is made up of several substructural microstructural features. And instead of further zooming in, let's take the other way around. So we all learned that a matter fundamentally is made up of atoms. So atoms have nucleus and they have electron cloud revolving around them. And then in crystalline matter, these atoms don't sit at random locations, but they form very structured and organize them in a very structured way. And as you could see here, these, for example, if you have to give an example, if you have a molten metal and then you solidify it, these atoms start stacking together in an organized way at a nucleation point. Now, the condition at one nucleation point is different from other, and that is why you could see that there's a boundary here between the two crystals. And these are called grain boundaries, and the region between these grain boundaries are grains. Now, the stacking of atoms is usually not flawless, which is why you have defects And these defects, especially dislocations at microscale, form the fundamental mechanism of deformation. If these defects were not present, then the metals would not deform but simply shatter like glass. And these individual grains together form the polycrystalline structure of a turbine blade that you could see here. So when we are speaking about the mechanical properties of a turbine blade, we are actually referring to the incredible hierarchy of microstructural features that we see here. And since different features are seen at different scale, different simulation techniques are also involved to simulate this effect of these features. At macro scale, you have multi-body dynamic simulation, which usually considers the connection between different components. And then if we look at a single component, we have macroscopic plasticity simulations, which are based on yield function and plasticity theories. On the other hand, where electronic structure of the material is considered, there we have quantum mechanics simulations, and then there is Newtonian mechanics, which do not consider the electronic structure, and we have discrete dislocation dynamic simulation at microscale, which only consider the dislocations and their impact on hardening. But clearly, the simulation techniques on this end, they are quite practically applicable, and they can reproduce the realistic boundary condition which is actually seen at a component level. But they lack predictive capabilities because they ignore the microstructural features. And the simulations on this end, they are quite physically grounded, so they are quite accurate, but they suffer to extend or to larger volumes or be physically applicable. So what comes nicely and ideally in between here is mesoscale. Mesoscale simulations acts as a bridge between the macro scale and micro scale. So they try to capture the physical detail from the lower end simulation and also be practically applicable for the macro scale simulations. So in this family of simulations for material deformation, crystal plasticity is one of the important simulation technique. So as I said, macro scale is, it connects macro and micro worlds, and it also acts as a perfect middle ground, but it also comes with many challenges. So it not just inherits the best of the both worlds, but also worst. I'll explain you why. Because at very small scale, you have the first principle simulations, which are physically quite grounded, but the problem is to set up a simulation, you need a very less number of input parameters, such as fundamental parameters like atomic mass, electronic structure, etc. Similarly, on the higher scale, you have homogenized macro scale models which use yield function. There again, it's quite empirical, but the number of parameters required to set up these simulations are quite small as well. But the problem is, since mesoscale acts as scale bridging, so here you see that the number of parameters required to set these simulations are quite high. And because the number of parameters are quite high, to describe the material, it means that it's challenging to identify them from the simulations, and also it's challenging to calibrate these parameters uniquely. So with so much promise, the challenges at these mesoscale are also quite high. And this is exactly what my thesis tries to do. So the aim of this thesis is to assess and refine the currently existing micromechanical modeling strategies in order to enable high fidelity digital twins of polycrystalline materials. So if I have to put this in very simple words, the goal is to make our simulations behave more like the materials themselves. And since the aim of this, the overarching objective is quite general, so it is made operationable by formulating the research question which are actionable, and these are based on targeted test cases. So here, before I start explaining the research question, I'll be making frequent references to the story that I told you in the beginning. So when the mission control engineers on the Earth, they got the news that the spacecraft, the oxygen tank had been exploded and damaged. Now they tried to simulate it on the ground. with the help of simulators. They did not start from an ideal spacecraft, but with the help of telemetry data, they first simulated the damaged spacecraft, and then they tried different scenarios to get insights from that. Similarly, materials also undergo different processing conditions, and these also have impact on their state, such as residual stresses or plastic state. Now, these data should be included in your simulation so that your predictions are accurate. So in order to do that, my research question addresses how we can enhance representation of material state. And this question asks, how can experimental residual stress data characterized by experiment be integrated into crystal plasticity simulations to improve material state representation? And this was done for FCC in Cornell. So a microstructure that was characterized from experiment was used, and this technique or method is designed particularly for the case where you only have residual stress data for this small subset of grains. But this doesn't stop it from using it for the case where the entire volume is characterized for residual stresses. So with this initialization of residual stresses was made in the volume iteratively through Newton's method. And as you could see here, the error on the y-axis decreases as the number of iterations increases, which shows that the residual stresses converge to the reference value that we provide. So this method also ensures strain compatibility and stress equilibrium, and also captures intergranular variation of stress and strain. So in conclusion, this method helps us to initialize residual stresses extracted from the experiment exactly into the simulations. So through this, it helps to improve the physical realism of our models. Next, when again drawing parallel to the first story that I explained, so when they got to know that the spacecraft was damaged, they used these two simulators that you previously saw in the picture. But these were not the only two simulators that were ever built by them. So even before the launch, they had built many different simulators which differ from each other on complexity, the level of detail that they captured. And then they tested all the simulators, got to know the strengths and weaknesses, and then they decided based on application which simulator is best, and these were considered as the final ones. Now similarly, in modeling, what we try to do here is we have a myriad of constitutive models, also differing in the level of detail that they capture. But there's a trade-off. The trade-off is the level of physical detail that you need, and also the operational efficiency of the model. So typically when experimental data is scarce, then operational efficiency becomes quite important. So this question addresses assessment of these constitutive models and asks how do different crystal plasticity models compare in reproducing mesoscale responses when benchmarked against experimental data. So for this, I used two types of crystal plasticity model. One, dislocation density based, which is physics based model, which captures detail of the dislocation structure, and the other one being phenomenological model. So here, the microstructure and the residual stresses from the first research question were taken and used it here. So the model were fitted, since the comparison or the assessment is done at mesoscale, the macroscopic data was used for fitting these models. As you could see here, the macroscopic data, experimental data represented by black markers, and the two models, blue and yellow, they were fitted on the macroscopic level. And then this load states that you see here from S0 to S6, so the mesoscale assessment was performed at these load states. But first, let me again emphasize the importance of having accurate initialization. So I want you to just focus on this gray lines, which shows the scenario where residual stresses were not initialized in the material. And as you could see here, on y-axis, the height of the bar show the modeling error, and without initializing residual stresses, across the different load states, you see that the value is high. So modeling error is quite high. So this again emphasizes the importance of initializing or correctly initializing the residual stress states. And then comparing the two different models, dislocation density based and phenomenological, they show comparable accuracy. So with this, the phenomenological model, although being operationally quite efficient with less number of parameters, showed comparable accuracy as the detailed dislocation density based model. Next, so the mission control, when they got to know that the spacecraft was damaged, they so the model that the simulator that they had were not originally modeled to work on a damaged spacecraft, state of the spacecraft, but it was adaptable and flexible so that they could first simulate the damaged spacecraft and then they could test different scenarios. Now, similarly here, good models should be able to not just perform in the area where they are calibrated, but also outside it. So for this reason, we try to improve the phenomenological model by so that they can perform not just in the area of their calibration, the domain of their calibration, but also outside the domain. So for this, this question is posed as how can phenomenological crystal plasticity models be refined and reliably predict beyond the monotonic and calibrated strain paths. So first, we first identified the scope for improvement, and then here we noticed that for the phenomenological model, especially the hardening coefficients, 4 decades old assumptions were used and had been continually being used now, till today as well. So we referred this as traditional parameterization. Now, these parameterization were based on the experimental data that was present 4 decades ago, and these are still being used till date. And then what we propose is interaction coefficient, which we obtained based on recent physical insights from the lower scale simulations. So the testing was done within the calibration domain first and done at two fronts. One, deformation behavior, where only active slip systems have play a part. So this is a correlation plot. On y-axis, you have the aim, and then on x-axis, you have two different model compared. And here, if for perfect correlation, all points should lie on this 1:1 line that is seen here. But let's compare, if we compare two different parameterizations here, for interaction coefficient, the high density regions are quite narrow and along this 1:1 line, which shows that the predictive capabilities of interaction coefficient parameterization is better than the traditional ones. And similarly, this was again tested along another front where hardening behavior was compared. And for this, both active and latent slip systems were used. And there, again, you could see that for interaction, the high density regions are nicely overlay on this line, 1:1 line. But for traditional parameterization, these high density regions have a best curve which is deviating from the 1:1 line. So again, even at deformation behavior and hardening behavior, what we propose, the interaction coefficient shows better results. Now, predictive capabilities beyond the domain of calibration. For that, we had to influence a strain path change. So that we did first by having a monotonic load. And here, since this was calibrated, so this is macroscopic stress versus strain. And since this is monotonic load, only 30% of the slip system in the volume is activated. As the wise man once said, Taylor, that you don't need all the slip systems to accommodate a deformation, but you need only 4 or 5 of them. So here, as you could see, all lines lie on each other, and this is expected as this is a monotonic load. And then we inflict a strain path change by loading it in the transverse direction. And here, you could see that it hardens or yields at a higher level because of initial hardening. And comparing, here I would like you to focus only on the red, which is the reference one, and black, which is the reference one, and red, the interaction coefficient parameterization, and the traditional one, which is orange. And the agreement between the interaction coefficient and the reference one is closer in comparison to the traditional parameterization. Now, activating even more slip system with the help of a shear loading cascaded on this. Here we activate about 65% of the total active slip systems, and here we also see that the interaction coefficient yields better response in comparison to the traditional. So we compared it against multiple fronts, one within the data domain of calibration and even outside, and we saw that the physics-based parameterization with the values obtained from lower scale simulations yield better results and also therefore demonstrate predictive capabilities. Next, multi-level calibration. So here the question was how to reliably identify material parameters for a complex deformation system as hexagonal closed back titanium, not just with the help of macro or mesoscale, but with the help of macro and mesoscale data. So since mesoscale models try to act as a bridge between macro and micro worlds, so for the calibration, you need data not just from one side, but also from both sides. So here we have a multi-level calibration, which is across the scale. I want to just show you why this is important. So I've compiled this two parameters, ratios of CRSS. First, let's focus on this orange line, which is the CRSS of basal by CRSS of prismatic. And here, this is a box plot. So 50% of the values ever reported in these 15 publications are within this range. So it ranges from 0.9 to 1.2. This doesn't seem to be that bad, right? But here, even a decimal point has a significant influence on the material behavior. Now, this is not, this gets even worse when we look at this blue line. Here, the range, 50% of the data reported is between 1.4 to 3. So the range is quite wide. And if I'm someone who wants to use such a data, and when I look it up in the literature, if the range is like this wide, then how do I decide which one to use? So the idea is that we need data not just from one scale, but we need data across the scale to calibrate the model. And we perform this material parameter calibration across scales for elastic constants. So I just wanted to show that we have mesoscale data and macro scale data and experimental data which are scattered, and then we, using an optimization algorithm, we fit the data and obtain elastic constants. And similarly, for plastic response, we fit the model not just at macro scale, but also with the mesoscale, macro scale data set. So with this reliable parameters, we also performed validation studies. So what we obtained from this is that reliable parameters for hexagonal closed packed titanium via multi-scale calibration. Now, using this calibration, using this reliable parameters, we can actually see the trends that we see in the experiments, whether they would relate, whether they would translate to just a correlation, or is there a cause for seeing those trends. So we try to look at, we try to see that. So the research question, the last research question asked, how can reliably calibrated models be employed to establish causal linkage between micro-textured regions, which is seen in titanium, and residual stresses in Ti64 alloy. So for this, this is often seen in titanium that after hot rolling, it has like a micro-texture region of soft or elastically stiff and elastically compliant grains, as you could see here. And it was seen that after machining operation, the residual stresses that generated after this machining operation had a hint of correlation with the stiffness of the material. or stiffness of these zones. As you could see here, we cannot statistically say anything about this, but it gives us a hint that there might be a correlation between the stiffness and the residual stresses. And for this, we used the reliable parameters that were identified from the last research question to study with the help of simple RVs that you could see here. And from this, from the simulation, we were able to reproduce the correlation that was seen in the experiment. And this was the correlation, yeah, just to show you juxtaposing. So correlation seen in the experiment and from the simulation. But still, there are outliers. And these outliers hint at not just elastic constants, but also other contributions to this correlation. And it was seen that it was not just the elastic properties, but also plastic properties which affect the trend of data that we see. And these are, of course, two are dependent on the orientation. So orientation plays a major part here and has an influence on residual stresses. So through this study, we were able to mechanistically understand what was causing such a correlation that was seen in the experiment. And thereby, we were able to bridge a microstructure property linkage, microstructure property relationship. So with that, I am at the conclusion of my presentation. So at the beginning of this presentation, we started with a very simple idea. The idea is to achieve reliable decision making, we need to have a digital twin which is closely mirroring the actual state and actual reality. And to do that, we try to improve the mesoscale modeling strategies so that eventually we have high fidelity digital twins. And in that, the first step was to improve the material state representation with the help of incorporation of residual stresses so that the physical realism of the simulations are improved. Next, we compared two different models, one phenomenological, which is operationally quite efficient, and other dislocation density based model. And it was seen that under data domain of calibration, phenomenological models perform comparable to the dislocation density based one. Next, we try to enhance the predictive capabilities of this phenomenological model by using physics-based insight, and the focus was outside the data domain of calibration. And we did that with the help of incorporation of physics-based interaction coefficients. And for a complex deformation system, such as hexagonal closed-back titanium, there, using this multi-scale parameter calibration, we try to mitigate the parameter ambiguities that are often seen from the data that is published in the literature. And with these reliable parameters, we were able to perform a structure property linkage even with the simple RV cases that we just saw. So together, these advances improve the mesoscale modeling strategies and also lay a foundation for high fidelity digital twins of polycrystals. So I have one more slide for the future directions, but I'll save it for later when we have interactive discussions. So with that, I'm at the end of my presentation. I thank you for your attention.
Okay, thank you, Nikhil, for giving a nice presentation, telling the story of your journey, your doctoral journey. Now we go to the second part of the defense, which is the questions by the examination board and the audience. First of all, I will introduce the members of the examination board, and I will do that in the order that they will ask the questions. First of all, we have Alexander Hartmeier, special guest from abroad. He's from the Micromechanical and Macroscopic Modeling Research Group or Department, Research Group at the Ruhr Universität Bochum in Germany. All the other members are KU Leuven members. There is Professor Neil Moulans from the Department of Materials Engineering. It will be followed by Professor Jentel Spolfs from the Department of Materials Engineering and Bert van Baal, also Materials Engineering. And then we come to the two supervisors, Professor Mark Seeveld. He's a co-supervisor from Materials Engineering. And then the corresponding supervisor is Professor Martin Diel. He has a joint appointment at the Department of Materials Engineering and Computer Science. Okay, finally, my name is Joris de Schutter. I'm from the Department of Mechanical Engineering, so I'm not an expert in the field. I'm just chairing this session on behalf of the Faculty of Engineering Science. So let's say Master of Ceremony. So I invite the first member to ask his questions.
Thank you. Yeah, first of all, thanks for a clear presentation and putting your work in such an elaborate framework. I think we could all learn a lot from that. I have a question concerning your term high fidelity twin. So how could you judge or assess the fidelity or the quality of a digital twin?
Okay, so this could be usually done by comparison with the experiment, but for that, the data required from the experiment is also quite extensive. For example, if you want to really have a one-to-one physical digital twin, then you need to have microstructure data. And also it depends on at what scale you are doing these comparisons. Because as you go lower the scales, you have stochastic mechanisms that could be activated or that could be seen in the data. So then the digital twin should be defined in a different way, and at macro scale, the digital twin would be defined in a different way. And I think it depends on what behavior you're trying to capture.
Mm. Where you said digital twin has the three levels. So there's always the real system, then your digital model, and the communication between the two. So let us assume we have a real system, maybe a component or what you showed, turbine engine. So how could the digital version of this look like, and I mean, which ingredients would you need there to have a high fidelity digital twin?
One would be we need a lot of sensors to first characterize it, and then the microstructure would be important. But then if you're looking at a very bigger scale, then maybe the microstructure features are all averaged out. So maybe a yield function would work. So yeah, for to have a digital twin, like for the communication channel, the processing condition that the actual component undergoes, for that, the sensors would be required. But at micro scale, the sensors are not really there. But okay, at macro scale, you have sensors for pressure and other temperature. But at micro scale, for stresses and strain, the sensors are not really there. So those would be quite important for the feedback loop.
And what would be what is the problem? Why don't we have microstructural actually, we have very good microstructural sensors, but why can't we use them per se for a digital twin?
But they are usually destructive. They are on the destructive samples.
Yeah.
And even the non-destructive techniques that we have are semi-non-destructive, because at the end of the day, you need to take a small cut from your actual component and then test it in a lab.
Do you see any way out of this dilemma?
With the current technology that we have, I don't think it's possible in the next the next few years. I don't think it's possible, but maybe with the X-ray techniques, with the strength of the energy of the beam becoming higher, and then with good post-processing techniques, we would be able to achieve this on the actual component and not on the smaller one. But that's like still further away from what we are now.
Then let me come back to the original question. How can we assess the quality of a digital twin? And actually, does the digital twin always have to be perfect, or how can we assess if a digital twin is good enough for the purpose we need?
Yeah, I think it depends on the application, right? So
Exactly.
if your application, if you're trying to model something at a very small level, like semiconductor interconnects on that copper interconnects, there the length or in the thickness, it is in terms of a couple of grains thick. And there, if you want to really mimic what's actually happening in one single component, is difficult because you have stochastic mechanisms, and this deformation can be different because of this stochasticity. But it also, well, if you have a large enough component, then these things average out. So digital twin would be more reliable when you have a larger scale component and without, and it also depends on how our constitutive models are formulated. For example, the models that I use typically smear out all these local stochasticity or discrete events and then say the plasticity is quite even.
So exactly, it's actually more or easier. The larger the system gets, the easier it is to describe.
Yeah.
To describe it, because you have then this statistical behavior helps you to describe it. But if you zoom in, it's more the individual behavior that matters, which makes things so complicated. And in that regard, in your presentation, you mentioned this multi-scale nature of material science actually and materials descriptions. So how deep, or you worked a lot now with crystal plasticity models.
Yeah.
Do you think we could make these crystal plasticity models much better by incorporating more information from dislocation or even atomistic simulations?
I think we can make these models as complicated as it can get, but the true challenge remains is how do we find then these parameters? So that would be more important, the reliable finding of these parameters, and also make sure that these parameters have a physical meaning. These are not just fitting parameters. So
you gave the example of this hardening matrix, and that you could have the coefficients as such. Do you think we could calculate these coefficients with the density functional theory, so without any assumptions and with a high fidelity?
For interactions of individual dislocations, maybe atomistic methods would work, but when we want to see the impact of a forest dislocation on a single one that is going through the forest, there maybe not atomistic, but discrete dislocation dynamics would work. So my idea is from the lower scale simulations, you take some insights and use it in a higher scale simulation, and then increase the scale of the event, and then again use this insight into crystal plasticity models.
Okay. And why do you say we cannot calculate or use the atomistic methods for everything, or to calculate these parameters directly for dislocation interactions?
Yeah, so currently these are computationally quite expensive. But also it depends.
And let's take a bigger computer.
But yeah, I mean, technically everything could be simulated with atomistic simulation. But then the question is
that true?
I mean, it depends on how big the computer is and how long you can wait for it. But the question really is, do you really need that kind of accuracy? Because typically, if your application doesn't require that level of detail, then I don't think it is really needed to model really physical parameters.
Yeah, then, I mean, the first answer, I would challenge this. It's not only a matter of bigger computers, but I fully agree with your second answer. It's not necessary.
Yeah.
And so we have to say, okay, when is our model good enough? But actually, there's so many atoms in a real system that you need a computer as large as the Earth also to simulate everything. So maybe finally, what do you, or the final question now, where do you think is the hardest challenge to get a digital twin in your area of microstructure property relationships, and what could we do there to improve our technology towards a digital twin?
Okay. I think the hardest part would be still at micro scale, because at macro scale, if we have enough computational resources, we could model bigger systems. But at micro scale, because of this stochasticity, you can never replicate one-to-one behavior that is seen in the experiment. But maybe I think mesoscale is also quite hard because it tries to be a bridge between two, and also to describe these simulations, you need a lot of parameters, and these parameter values also need to be identified uniquely. So the challenge really lies in mesoscale simulations, I think.
Parameter identification.
Especially for dislocations, because you try to characterize this as densities or scalar values or higher dimensional density like variables, but getting aid for this from the experimental side is also quite difficult, non-destructively. So I think the bigger challenge is still in the mesoscale.
Okay. Thank you. I completely agree.
Thank you.
And I pass on the microphone.
Okay, thank you. Yeah, first of all, Nikhil, I also appreciated very much the way you present your research and the way you link it to history. And
thank you.
I first had a question about one of the main challenges of mesoscale modeling, as you mentioned, it's the number of input parameters. But I was wondering, of course, you can use a lot of input parameters. You can formulate very complex models. But aren't there ways to reduce the number of parameters that you need as input?
Yeah. So if we compare phenomenological and dislocation density based, in dislocation density based model, the result or critical result shear stress is dependent on the structure of dislocation and density of dislocations and how they interact. But in phenomenological model, they added an abstraction layer on all of this and said, okay, let us have a single variable critical result shear stress, and then let's somehow fit this variable from the experimental data. So there is an abstraction layer from physics-based to phenomenological. So in my opinion, simplifications are indeed possible, but then not every time it's as simple as fitting one single parameter. Sometimes if you need predictive capabilities, then you need insights from physics when unknown behavior is seen in the model.
But I think we agree that there is usually a way to reduce this number of parameters to a feasible extent.
Yes.
I also think that there is another very important challenge in mesoscale modeling, and that is to know what to simulate, because usually we are looking at a macroscopic process, and if you zoom in, well, you can zoom in, look at many positions in your macroscopic part. You can look at many phenomena. My question is a bit like your simulations that you did. They were just defined like that, or was there a kind of way or reasoning that you decided to simulate these particular phenomena?
Okay.
Based on the macroscopic process that you see.
So the first data that I presented with the 3D microstructure, that was part of a challenge. And then we wanted to really see how different crystal plasticity models are able to achieve mesoscopic predictions. So that was the motivation for the first one.
But if we look at a study where you start from the macroscopic process, and you want to learn something about the macroscopic behavior, then somehow, well, you cannot simulate the whole macroscopic part, and each position will maybe behave in a different way. So how to decide what you will simulate on the mesoscale to have the good information to control the macroscopic process?
For the last study that I presented, we used so the actual material is at a macro scale, so it has thousands or millions of grains. But we then did or RVE, representative volume element based simulations. So with that, we tried to capture the salient features that is seen at macro scale and then try to bring it to the RV based simulation and try to see how certain microstructural features influence the state of the property of the material.
Yeah.
And then we simply started to add complexity. From a bicrystal, we moved to a macro zone with polycrystal. And then our insights improved. So I think, yeah, it depends on simplification. So
and you did it through the RVEs, in fact, then?
Yeah, for the last case, it was...
So you assume your material is behaving similar everywhere, then?
Yes. Yeah.
Okay, yeah. But can you imagine that there are maybe certain macroscopic processes where that would not work? And how would you
so
do the...
in that case, we used two different RVs. One was a bicrystal, which corresponded to the ideal scenario of having two microtexture region right next to each other, and this was infinite because it's an RVE. And then to add complexity to it, because we also saw that at other regions, it was not only like lamellas, but also there were other intermediate orientations involved. So for that, we increased the complexity by having a random polycrystal. So this is not the end. So we can again increase the complexity and make it more representative of the actual state.
Yeah. Okay.
Yeah.
Okay. Thank you. Then another question is maybe more general. So you have talked about, I assume you need a lot of compute power to do your simulations. Probably you also need a lot of memory in the computer. You need a lot of data. What is the key bottleneck for your simulations of these three?
I think the optimization there, I really faced computational challenges. Because the optimization, we used a Nelder-Mead method, and then for that, for every run, it has to calculate lattice strain of all the grains, and then we throw away most of the data and use it only for the specific orientations that we are interested in. So there, I think the optimization could have been improved, but for crystal plasticity itself, with the compute servers that I used at VSC, I did not really feel that there was a computational bottleneck anywhere.
Okay.
Because we use fast Fourier transform, and it seems to be quite.
So the
fast.
computation was not then the data was the bottleneck, or I'm just interested in what was because you need all three.
Experimental data is indeed quite.
So if you would have more data, you could make the model better. You would use more compute power, but you have it available. But so what you really need is more data, and then you can improve. While for the optimization, you would need better computers. And then you
or
can
better algorithms, or better implementation of
Yeah.
algorithm. Because I just wanted to get it working, so that was slightly slower way, and I think that could be improved significantly.
That's my question. I don't know if I... well, one more question, or... then I was also interested about the initialization. So it was your first research question. I think also with microstructure simulations, it's always a challenge to have the initial microstructure correct and complete in the model. So you included the residual stresses. You think that was enough to have an accurate simulation, or do you think...
So in this case, we have explicit microstructural information like grain shape and
so that was
grain
also
size.
there,
And then we implemented residual stresses, but the data was there only for a small subset of grain. So as an improvement from experimental side, if we had data for all the grains, which is now possible with the recent characterization techniques, it would be nice to have like a full volume initialized residual stresses. And even
how much would it improve? So what I actually want to know is how important is it to have your initial microstructure exact?
This is quite important in my opinion, because let's say if you want to predict fatigue live, especially high cycle fatigue, there the models that we currently use only use the data from first few simulations, first few cycles, and then extrapolate this. Now, as we saw also here, residual stresses significantly impact on the behavior in the elasticity dominated regime.
Yeah.
And if the first few cycles, if the stress values are quite off, then the fatigue life will be impacted significantly. So for fatigue, it would be very important to have even the smallest details such as residual stresses incorporated correctly in the entire volume.
Okay. Okay.
And also it will again impact on the yielding of certain grains. Yeah.
Okay, thank you.
Yeah, thank you.
Thank you, Nikhil, for a nice presentation and learning us something about Apollo 13. Your thesis is mainly simulations and, of course, trying to compare against the experiments. And in a thesis like that, it's very common to criticize your simulations, to identify all the issues. But I actually want you to do the other thing, criticize the experiments. I remember in your thesis, you mentioned one thing, which was high volumetric contractions in the experiments. Is there a way to resolve that? Or do you see any other experimental issues that may affect the comparison with your simulations?
Yeah, so that actually was quite interesting behavior that we see in the experiment. So I wanted to investigate more about it, and thankfully Martin's other project was had an opportunity to perform similar experiment, but maybe an improved version of it. So scanning 3D XRD. So 3 weeks ago, I was at Grenoble performing or helping people who perform these experiments. There I got to know a lot about it. So the box scanning strategy that is used there, so that identifies the center of mass of each grain and then somehow extrapolates the size of the grain. But that is not ideal because we see that this really high volumetric contraction in the data. But nowadays, they have an improvement in this strategy. So they use like a pencil beam and then characterize each voxel. In the older method, we used to get data for the averaged out data for the entire grain. But now, because of this new characterization method, we have data for individual voxel. So I think that would improve, and I'll be working on that data set in the coming months.
Is that ID11, or which beamline is that?
Yeah, ID11, yeah.
Okay, interesting. Then you are mainly simulating plasticity,
yeah,
and you're not really trying to simulate fracture.
Yeah.
Now, you also have a voxelized model, which is generally seen as not a good way to model fracture.
Yes.
What would you need to do in order to be able to model fracture? Would you need to go away from voxelized models? Is that even possible in your approach?
There was one study which used phase field and fast Fourier transform, the solver that we use. But for damage, what we do here sometimes is use indicators of damage instead of really modeling the damage, because we are still in the area of plasticity, which is, okay, we don't really consider the damage part of the material behavior. So we try to have like indicators which suggest that damage might occur here. But yeah, I agree that with this voxelized, I don't think it's possible or ideal to have like a crack nucleation or something like that. But damage, yeah, if you have, and also this method is quite different from finite element, where usually if a cell is fully damaged, it is deleted out, so you have a void. But in this case, we cannot have empty material in this because it requires, the solver requires it to be periodic. So we can have like a elastically very compliant material, but yeah, there are like limitations for this method, and voxelized is one of the limitations.
Okay, thank you. I will pass on now.
Okay, thank you. Okay.
Yeah, okay. Accidentally, it was in the wrong position. Good. So in the conclusions of your chapter 4, you write that, well, you suggest to incorporate relative interaction strengthening ratios identified through lower length scale simulations or, where possible, latent hardening experiments. Yeah? And then I was a bit wondering how you would tackle this issue. So what would you model exactly, and which kind of latent hardening experiments are you thinking of?
So these latent hardening experiments were initially used in 1960s or 70s. So what they tried to do was first apply load in one system so that the other slip system is hardened enough latently, and then they used a different orientation of the sample and then load this latent hardened system. And then you would see how much it has already hardened. So from that, you could infer from hardening of one slip system, the geometric relation between them, how much, well, what factor it has hardened more because of it being simply latent. So that would be, that experiment was used like for 4 or 5 decades ago, but I'm not sure if people nowadays use these experiments to really identify latent hardening parameters, because it's quite difficult, first of all, to load and specifically target the slip system that you are interested in. And especially when you have complex material, it even gets more complicated. Yeah. So I just did not want to rule out the possibility that latent hardening experiments are not possible at all to identify. So that is why I mentioned, if possible, with latent hardening experiments.
Yeah. But you think there still is an important role for such experiments? Do a kind of intermediate evaluation of your lower length scale simulations?
I think, yeah, that could be, for simpler cases, I think validation of such simulations can be made with these experiments, but only for simple cases, because quickly the many slip systems will start interacting with each other, and the interactions will get complex. So yeah, I think it's possible for very simple cases, but not for, especially for cases where multiple slip systems are involved.
Okay, thank you. So in the text you also talked several times about stochastic effects. Yeah? Yeah. And I was wondering, how do you think you can best model stochastic effects? Would you incorporate some kind of stochasticity in the model itself? Or do you just resort to, let's say, considering large structures with lots of different points, and where the stochastic effects will pop up by themselves?
I think both are possible. Like having a seeding point already in the volume, but this seeding point chosen stochastically, that is a possibility. But also on the modeling side, in the formulation itself, if you have like a parameter which suddenly have this stochastic response, stochastic mechanism gets activated, that is also possible.
Yeah. Would you give preference to one of the two approaches?
I would have something in the constitutive behavior than in the geometry, or it being dependent on the model. So I would prefer the one in the constitutive behavior.
Mm-hmm. Okay. And then a bit a general question. If you want to tackle and look at a new material, would you, well, you have these highly complex models and you have the macroscopic models. Would you, in which direction would you follow consecutive models? Would you start off with the globally macroscopic ones and then only go deeper if you need it? Or would you start off with an as accurate as possible model and then slowly or see what is important at the macroscopic level?
Yeah, so I would do the latter approach. So first run a full simulation with a simple model and identify points where you might think that these are critical area, and there you can actually go in detail. Because especially for phenomena like damage, where the weakest link is quite important rather than the average behavior. So maybe it would be like a layered approach where you first simulate entire with a simpler model and identify the critical points and go more deeper into such points.
Yeah. So the problem actually seems to be that in advance you do not know precisely how your digital twin should look like.
On the modeling perspective, yeah, we don't actually know, because we can simulate everything with a very detailed model, but the question is if it is really necessary. So we can like divide them into zones where these detailed simulations are necessary, and they're there. You could do it.
Okay, well, thank you for the discussion, Nikhil.
Thank you.
Thank you very much, and thank you very much, Nikhil, for your nice presentation and for all your nice work. My first question is on your additive project, your first sub-project that has actually grown from a very interesting scientific format, I would say, namely from a challenge. You started a bit too late to really still participate in the challenge, but what I would like to know whether you could learn from the interaction with the other teams. So you have made your own model, you've made your own results, you've assessed where it did not give the results that you hoped for, and where one might still improve your model. Can you compare that to the findings of the other teams, to the assessments of the other teams? Have they published their shortcomings? Have you interacted with them? And in which sense has this been helpful for your own work?
Yeah. So I think I had these two publications which I referred when I first started working on this data. So both show similar accuracy as we do. So they use different solvers and different packages, but still our accuracy is comparable to theirs. So that becomes like a benchmark data, and we could say that all our solvers are implemented in the right way because we all get the same accuracy. And then this idea of stochastic mechanisms impacting material or elastic strains at mesoscale, I got this idea from a conference. So I met a person who also used this data, but he participated in the challenge, but he did not win, but he participated. And then he had a paper which also mentioned about the stochastic mechanism that could be active and resulting in the error that we see. So from that, we could take insights and further investigate in that direction, whether if we artificially try to engineer this kind of stochastic mechanism has happened in our microstructure, how does the material behave from there? So these interactions with the other participants have like helped us to further improve this work that we did.
And the shortcomings that were identified by the others, have you come to the same conclusion, to the same needs for improvement of the models, or?
Yeah, there I think none of the participants actually went this deep into the behavior, mainly because for us, we got the insights that stochastic mechanism could be a reason, and then we tried going deep into that part. But they suggested in their paper that it could be the reason. But other paper, yeah, usually the focus was more on the modeling and not really what mechanisms could be possible, the reason for not having, for the discrepancy. Yeah.
I see. Thank you. And then I have a second one, a bit to tease you. Jentel has invited you to not only criticize your own modeling approach, but also the experiments. I would like to do something similar. You are basically criticizing your scale. The terminology that you have used and which is widely used in the community is one of contrasting physical models versus phenomenological models. Density functional theory, Professor Hartmeier has mentioned it, is exact at 0 Kelvin. As soon as it is not 0 Kelvin anymore, it's based on assumptions, approximations, similar. Molecular dynamics is using empirical potentials.
Yeah.
On the other hand, if you're looking at the classical yield loci, von Mises, for instance, makes use of an assumption which physical quantity should reach a critical value such that plasticity be activated. So is there actually that much of a contrast between physics and phenomenological, or what is your opinion about that? Are the phenomenological models really only phenomenological, and are the physical ones maybe more phenomenological than they claim?
Okay. For the first question, phenomenological, I think it depends on the parameters. So even in phenomenological model, there are physics-based parameters like CRSS, which is one of them, and then the amount until which a slip system can harden can also be considered as a physical parameter. But then there's a power law exponent, which is purely fitting parameter. So, okay, it has a mix of both phenomenological fitting parameters and physics-based parameters, and it depends on how we calibrate them. We can achieve the same response using number of multiple combinations of these parameters, but the focus should be on using really physical insights to choose the value and put a realistic bounds for these parameters. On the other hand, we have dislocation density based, which has like 20 parameters, but usually the question when we set up a simulation, do we really confidently know all the parameters or the values of it? And typically, this is not the case. So we assume a value for many parameters, and this becomes, and then we try to fit the data and change these parameters. So there, even in physics-based models, we fit the data as we do it for phenomenological models. So yeah, I think the improvement there would come fitting how we use these parameters to fit the model. So that is quite important, I would say.
Thank you.
Thank you.
Yeah, Nikhil, also many thanks from my side, certainly for the nice presentation today, and for the rest I think I have time later. You already discussed a lot about the model or the microstructure that you used in the first case study or in the first question. And now you mentioned you did already follow-up experiments in a way. So what will we do different? So how will we start modeling the data that you have now in comparison to what you tried maybe 4 years ago when we first looked at the data set that was openly available, but in a way a little bit unknown to us?
Yeah, so the data set that we got was not raw data set. So it was processed, and it was from like couple of terabytes. It was processed to maybe hundreds of megabytes. But now in this study, in the future one, what I'm gonna use is this couple of terabytes, and I'm really gonna understand how this is processed so that we have what is really needed, that is to model. And based on my experience when I was in Grenoble, I saw that the post-processing is a bit shaky because you have not the direct information, but like intensities on the detector. And you have to back calculate these grain shapes and also strain values from these intensities. And a lot of things can go wrong in this. So maybe it would give me a chance to really see how post-processing works, and then also maybe compare at times the error that might have occurred in the first raw process data that we used. Yeah, that would be my answer.
Yeah, thanks. I'm looking forward to that.
Okay, thank you to all the members of the examination board. Nikhil, normally the chair doesn't ask a question, especially since I'm from another field, but you teased us because you said you had presented some slides about your future work, a structured overview.
Okay.
While some of these points may have come across during the discussion, I would still like to invite you and present to us and the audience this overview of future directions.
Okay, thank you. Yeah, so the first direction which could extend this research would be what is really important in mesoscale modeling, as we saw, is data-rich experiments. Because when we calibrate, we cannot just have data from one single scale. So we need data across the scale. And for that, these data-rich experiments are really the way forward. And then another important point that we just discussed is one needs to enhance the visibility of this data. Not just the processed one, but however, yeah, it's a couple of TBs, but the raw data should also be made public. Then somebody who is interested in this work or somebody who finds that it's not really adding up, they can really look into this raw data and see why it's processed in the way it is processed. And either this would be because of this step, it would one could identify that there's a bug in the post-processing, or it would lead to a better understanding of mechanisms. It could be that our model is simply not able to capture the mechanism that is there in the experiment. So either ways, it would be good for the scientific community if it's open. And then, yeah, I think this we have also covered, that having physically meaningful parameters are quite important. The number of parameters are not that important, but really calibrating them based on what we see and physically bounded values, that is quite important. And yeah, improved, okay, this one I don't think I have covered it. So at mesoscale, we have stochastic responses or stochastic information in our data. But the problem is the simulations. If we want to simulate stochastic behavior, how would we know which behavior has a good correlation with the experiment? So if we compare 1-to-1, it's not possible that we have an exact match with the experiment. So for that, we need to come up with new and improved strategies, because like 20 years ago, comparing macroscopic behavior worked. But now, since we have data at very small scale, we should somehow find a way to reliably compare different models against the experiment. So this would be like the few future directions in which this work could further go.
Okay, thank you. Can you show the Teams meeting, or what do you have to see if there might be questions from online?
I don't have an online one. I just have a live streaming.
Okay.
Yeah.
Okay. Ladies and gentlemen, as I announced earlier, the Faculty of Engineering Science, they pay a lot of attention to interaction with the public during this defense. So I would like to invite you. I heard for online is only streaming, they cannot ask questions, but invite you here present in the room if you have a question to ask it or give a comment to the work of Nikhil. Yeah.
It's already on. Yeah. Well, thank you for the presentation. It was really clear. You had a presentation of the residual stress data, and there were only few grains.
Yeah.
But then for the simulations, you used only those 20 grains, or was it there a representation for the rest of the microstructure?
No, for simulations, I used all the grains, but the residual stresses were only incorporated in these grains. But then we had to use like an equilibration, and then this had to be done iteratively because there are surrounding grains. If you initialize it in just these grains, then it would be incompatible and the volume would be not in equilibrium. So for that, we had to equilibrate it so that we iteratively achieve the experimentally characterized residual stresses in these 28 grains. But the surrounding grains, they all now have a residual stress because of accommodation of these residual stresses in these grains.
Okay. Yeah. Thank you.
Thank you.
Is there any other question or comment? If not, then the examination board will now withdraw to make their final decision. Don't run away, we won't take long, and we will be back for the graduation ceremony.
Thank you.
Okay, please be seated. Nikhil, maybe you can stand there so that we can address you. Ladies and gentlemen, dear colleagues, I have the honor to inform you of the outcome of the deliberations of the examination committee appointed for the examination for the degree of Doctor of Engineering Science, PhD. Nikhil Prabhu has submitted a thesis to the faculty entitled Micromechanical Modeling Strategies Toward High-Fidelity Digital Twins of Polycrystals. And this in order to obtain the degree of Doctor of Engineering Science. He has defended his thesis in a public session before the examination committee. Dear Nikhil, the examination board has determined that you have met all the requirements prescribed by law and by the university regulations for the doctoral examination. By obtaining the doctoral degree, you commit to act in accordance with the basic principles of research integrity as described in the All European Academies European Code of Conduct. And these principles are reliability, honesty, respect, and accountability. And in a few minutes, you will receive your diploma and you will sign not only for the receipt of your diploma, but also to express that you will comply with these basic principles. Therefore, and on behalf of the Director of KU Leuven, I confer upon you the degree of Doctor of Engineering Science in Materials Engineering. And to make this legal, I also have to make these announcements in Dutch. Bijgevolg, en in naam van de rector van KU Leuven verleen ik u de graad van dokter in de ingenieurswetenschappen richting materiaalkunde. The secretary, and as Professor Swals will now hand over the diploma to you, and you will sign for receipt. So, and while he's doing that, we can already congratulate the doctor and give him an applause. Congratulations. The official session is closed, but the corresponding supervisor, Martin, will address you and give a laudatio. And after that, don't run away, we will make a photograph together. Yeah. Okay, you will sit down and listen.
Yeah, so, dear Nikhil, first of all, congratulations. Very well deserved. I'm very happy to stand here and tell you that. So, it was mentioned Nikhil did his master in Sweden. What was not mentioned was that he was actually working for IKEA there. So he did his master thesis in IKEA. Not in IKEA, but he worked actually on, you might guess it, on parameter identification, in thermoplastics actually. So I guess what Jentel is also working on, the fields are not so different. So he applied for the position that I offered, and I think I offered it actually before I really started here. With some help of colleagues from computer science mainly, I could start filling out the positions, and of course Nikhil was eager to start, I was eager to start, but it was taking a little bit longer than we hoped. And then I think you started in 2021 in January, right? And if you remember what was at that time, so it was COVID lockdown. So I think the start was was different than we both anticipated. But you very well did it, and I think in the end, also looking at the time scale, it worked out quite nicely. And there's also something that most of you know. So Nikhil also didn't only manage to finish his PhD in this now almost 5 years time, let's say 4 years and a half, but he also got married. So I think, looking back from this time, this is certainly important, but to be honest, maybe only second important thing that happened since then in your life. But yeah, I'm happy to contribute to that. And of course, it was not only me, but yeah, with Mark and the supervision committee, also from my side at this point in time, many thanks for helping and supporting me to get started and working on Nikhil's thesis and giving feedback and so on. I mentioned it, so Nikhil's thesis was, or Nikhil's hiring was done on a startup grant, and this is something that we, to some extent, unfortunately don't have so much anymore. It was money without a clear topic, without needing to impose on Nikhil what he wants to do. And I think the initial topic was around cyclic modeling of aluminum. I don't think we have heard anything about cyclic or aluminum, maybe cyclic, maybe not aluminum today. And I think that really shows Nikhil's qualities, that he can find his own topics and contribute to the outcome or contribute to the scientific community independently. So that's really something that I appreciate, the ability to work on topics that you define. And I think we also saw it in the thesis. It was, Nikhil's thesis. It was not me imposing you to do something. So, many different topics. Parameter identification. Also, what was maybe not so super clear from the presentation today. So Nikhil also worked a lot together with colleagues here. From with Akshay and Pushkar from materials engineering. That is also something that is very valuable and important, I think, in general, but also for a starting professor who needs to make up connection, having someone like Nikhil who takes the opportunity and shows experimentalists that simulation can be helpful and also understands what they are doing. So in the end, Nikhil used a lot of, and you used a lot of the simulation methods that we have. Initially, the plan was a little bit to develop more things, but even there, despite the things that we had were in general okay, Nikhil is a very careful worker, so he also spotted some glitches, bugs in the software that we had, and then also contributed to improving them. And that is also something, a big quality to really dive into the details and then pinpoint, okay, look, this is not going as I would expect it, so let's discuss forward and backward. We also tried that in the end for the experimental results, which are probably also having some issue. And we couldn't really resolve that. As you mentioned, the raw data is not there. Also, the person who did the measurement doesn't have it anymore or cannot access it. That's not really clear to us. But in the end, it was again like saying, look, there's something that we don't really understand. We should dive into it. And with the new work that you're now doing in a very well-defined project, we still have the chance to resolve this question. So many thanks again. It was a pleasure to have you as a PhD, and it's also a very big pleasure to have you longer. So I really appreciate that, and I'm looking forward. And that is what I have to say. Thanks and congratulations again.
Well done. Thank you. Yeah. Hello. Okay. This is mostly impromptu. I haven't really prepared for this. But I came to Leuven with a dream, and today I felt that that dream has finally fulfilled. And this wouldn't have been possible without the support and help of many people. Especially when I came here, it was COVID. as Martin mentioned. So maybe it was 2 days when I came here. I walked past the old city hall, and this was the picture I had taken there. It was very empty. I felt like I was in a ghost town, but okay, it was COVID. And once the COVID restrictions were lifted, I never saw it in that condition. It's filled with students. When it was COVID, I walked past Audermarkt, and I never imagined that there would be a bar, like a line of bars there. But now when I walk, I wish it would be sometimes like this during COVID as well. So recently, when I was scrolling through LinkedIn, I got a notification that it mentioned, congratulate Martin for his completion of 5 years at KU Leuven. Then I was like, wait, I started PhD, I'm almost defending it, and Martin started only like 3 months before I started here. So Leuven and KU Leuven both were equally new to us, and then that gave us an opportunity to explore the university intricacies and bureaucracy together. So the first laptop, the KU Leuven laptop that I got was 5 months after I started my PhD. So you should be very glad if you're getting it in 2 weeks nowadays. So again, it was my first day at KU Leuven, and I did not know what to do. I texted Martin whether I'm supposed to be at the department or whether I start working from home. Martin traveled before that day to Leuven, and then he got to know that there is a change in quarantine rule and he cannot come outside anymore. And then I vividly remember this email from Martin. It mentioned, I just traveled, so I cannot come outside because they'll, if I violate, I will have to go to jail for 6 months, which cannot be accepted at all. But otherwise, I can pay 500 euros, which I find it okay. So when he said that, I felt like, okay, this is a very interesting personality. So I had a very good impression of Martin there. So in addition, we also had like a wedding party organized by Martin and Fee. So also thank you very much for organizing the wedding party. And also you showed your pizza making skills then. So I was quite impressed with the pizzas as well. And also I would like to thank my computational material science team because of the numerous coffee meetings that we had and also the fun that we had during these meetings. And it was during COVID and the restrictions were almost lifted. And this hike, Numa hike, was one of the first Numa hike that I attended. And it was in Mountain River near Spa. And I remember this hike not because it was my first hike, because we had to somehow walk past the river when it was very slippery, it was raining. And since it was very challenging, I remember it quite fondly. So I thank again Tom and Inyas for organizing so many hikes and Sanaz as well. And it was really quite memorable. And I did not just hike, but I also played a lot of volleyball. And what is the fun part of it? Playing with colleagues. So we also participated in many volleyball tournaments. For the last 2 years, we did not really win, but this time we almost won. We got 3rd place in a volleyball tournament. So that was quite enjoying. The winning moment was quite memorable. In addition, we also did mountain biking and also adventure park. So, and I would also like to, this is Numa ritual that we do it every year at the department building. And also the coffee train, it was quite special. In the last years, I did not join coffee trains all the time, but before that used to be my getaway from research. And a special thanks indeed should go to Vince, who traveled all the way to India to attend my wedding. Here's the picture of Vince in India attending the wedding. So thank you, Vince, for doing that. And finally, okay, so these are not NUMA colleagues, but friends outside work. These are quite important to keep my personal mental health in check. So thanks, Anjana and Nishant, for being there. We explored many number of restaurants in Belgium. And yeah, through that, I gained a lot of weight, so I had to play volleyball to make up for that. But thank you very much. And also, discussing or communicating with you in Kannada also helped me to feel that I'm not away from the hometown. Okay, and the next set of people who are quite important in my personal life are my parents. So this picture was in 2018 when I first, it was my first flight to Sweden, and it seems like a long time ago now. But I would like to take this moment to really thank my parents, because sending a son to Sweden was a big financial decision. And my parents, when I expressed this idea to them, they never had a second question. So they were like, okay, you are allowed to do whatever you want, we'll support you with everything. So that I'm very thankful to them. And today, whatever I am, I owe a big part of that to my parents. And also my brother, from playing together to supporting our families, my brother has played a big part in what I have done. And I would also like to take this moment to remember a sad part of not being with family and being away from family is when you lose them permanently. So when I was doing my master's, I lost my grandfather and also my uncle. So that was a bit sad, but okay, that was a sacrifice for what I have, what I am. That was the sacrifice that I had to give to be here today. And then, yeah, like Martin mentioned, so this year was quite special. This and the last year in December, I got married, and my brother also got married. So our family expanded, which was 4 before, now we are 6 with the addition of 2 beautiful and supportive people. And then since, yeah, marriage, I also have an extended family now with my in-laws who have always been quite supportive, especially with the implications that a PhD had in my personal life. So I'm quite thankful for them as well. And finally, my wife, Lakshmi, the love of my life. So when we first met, I was almost on my way to do my master's. So that was 6 years ago. And since then, you have been there for all the ups and downs. You have supported me, encouraged me, and I'm quite really thankful for that. And I don't think words can express how much thankful I am. So, yeah, during writing of my thesis, you were there physically here in Leuven, and you are quite supportive. And maybe because of the support, I ended up writing a thesis which is 270 pages. Otherwise, it wouldn't have been that thick, I think. But yeah, thank you very much. I'm pretty sure that I've missed many names, mentioning many names. I'm thankful for Pushkar and Akshay for the nice collaborations that we had and also insightful discussions. And also thank you, Mark, for also many discussions that we had. I would also like to thank the jury. And yeah, and also thank you for people who have helped me to arrange the reception. So because of them, I think the reception is ready. So I would invite you to please, together with me, celebrate this occasion through this reception. So thank you.